All right, 14.5 cylindrical coordinates. We'll say cylindrical coordinates and integrals. So the point of this section will be to talk briefly about cylindrical coordinates and then to see what ramifications this has upon integration. So cylindrical coordinates themselves are fairly simple. We'll talk about them briefly and talk about a few objects in cylindricals. So the idea here is that x and y get replaced by r and theta, like polar, but z remains. So the x and y get replaced by r and theta. But we still keep z. So visually, the xy plane is now r's and thetas. So r and theta here, and z still up and down. So this isn't overly difficult. We're not going to worry about plotting points or anything like that. The key thing that we need to look at is to look at some of our basic objects, basic three-dimensional objects, and see what they look like when they're written in cylindrical. So let's say, what are some basic objects? So we'll just plow through a few examples. So consider r equals 2. So in polar, this is just a circle, but in cylindrical, we gain a z. Since z isn't listed, z could be anything, so this becomes a cylinder. So in polar, this is just a circle like this. In cylindrical, we have a z, which can be anything. So the result is a cylinder. So here's the circle. This extends up and down forever. So a couple similar examples. Familiar circles. R equals 2 cosine theta. Is a cylinder. So the way to see this one is in 2 dimensions we would have a circle on the sort of to the right of the x-axis. So here's the 2D case over here. Alright, because 2 cosine theta is like this in polar. So this picture, this circle is this circle. So we extend it up and down forever and ever and ever. So similar example, r equals, say, 2 sine theta, also a cylinder. But this one is now to the right over here. And extends up and down forever. And the 2D version, or the polar version if you like, if we were just doing polar, would be this. So in both of these cases, like in this lower case, this extends 2 and along the y-axis. In this case here, this extends 2 in the x-axis in the previous case. So a few more. The paraboloid. that we know and love. First one we overdrew, z equals x squared plus y squared. This becomes z equals r squared. That's it, very simple. But it is a paraboloid. Couple more. We'll do two more quickly. So the cone, z equals the square root of x squared plus y squared. This becomes z equals square root of r squared, so z equals r. So ridiculously simple looking equation for this cone. But notice this makes sense because what it says is that the radius and the height are tied together. So as we get higher up, the radius gets larger. So radius equals height, which makes sense in the picture. The higher up we are, the wider it is. And theta could be anything, because no theta is given. So one last example. So consider x squared plus y squared plus c squared equals 9. That's a sphere. Right here. So this in polar, or in cylindrical rather, this becomes x squared plus y squared becomes r squared. So we get r squared plus c squared equals 9. Now that sphere is made up of two hemispheres, top half and the bottom half, so we can actually calculate those. So the top half, if we solve for z, we get the positive square root of 9 minus r squared. And the bottom is the negative square root of 9 minus r squared. So a couple of other familiar shapes that have unfamiliar cylindrical coordinate representations, if you like. So then the next question is like, okay, great, so what's this got to do with integration? So three triple integrals. In cylindrical. So the idea is pretty much like in the previous section. We have a D that's between a floor and a ceiling and defined on an R. So similarly to 14.4, this is what we have. We have D as follows. So we have an R in the XY plane. The difference here is that R is going to be best in polar. Right? So here R is in polar, or best. But otherwise everything's pretty much the same. We've got a floor function and a ceiling function. And then we've got a solid which lies between those. That's our D. And so the result is that if D is described this way, then we get the following. Now I'm going to make a few notes about this, so we want to be sort of very careful here. So the integral over d of f of x, y, z, dv becomes the following. So the altitude integrals, those take care of the r. So if you remember the way we did those, an r in polar is taken care of with two angles and then two functions, one which is closest to the origin, one which is furthest from the origin, so near and far. The innermost integral, those are the z's. So this is floor and this is ceiling. Then we have the f. This may have x's and y's. The x's need to be substituted r cosine theta. The y's are sine theta. The z stays the same. Because we're kind of going into polar, we have to pick up polar r. And we have a dz, dr, d theta. So a few things about this before we give an example. Important things. So these two, these describe r in polar. So next to the floor and the ceiling, those, well, they're the floor and the ceiling, but here's the kicker, is they must be in cylindrical. In other words, no x and y. We'll see what that means here. In here we replace x and y. Shouldn't be an x and a y in sight. And over here we have the polar r. So let's look at a couple of examples, see how this works out. So moving back to the left, let's do the following. Let's say let D be, and I'll describe D. It'll be inside r equals cosine theta. We know it's a cylinder. It'll be above z equals 0. That's the xy plane, and it'll be below z equals 3 plus x squared plus y squared. So a picture of this. Now what we'll do is let's evaluate the triple integral over d of, say, x dv. So the solution. So here's a picture. A few pictures. So the solid itself, the d itself. So r equals cosine theta, that is the cylinder. That is this cylinder. So we're inside that cylinder. We're above z equals 0, so we're above the xy plane. So that's above this little plane down here. Don't really need that, but that's okay. And then we're below 3 plus x squared plus y squared, which is a paraboloid. Opening up at 3. So the solid that we've got is basically in here. Let me not do that in red, let me do that in green. Is this. This is our D. But what we can see here pretty easily is that z equals 0 is the floor. The paraboloid is the ceiling. And the R itself is described by the cylinder. So R is defined, if you like, by the cylinder. So this is the R. Do that in red. That's this guy. So if that's a bit confusing, the way to see that is if I redraw the picture. So if you're not sure why, if you're sure why, you're good. If you're not sure why, the way to see it is to redraw this. Just to sort of rethink it briefly, would be to think of it as xy plane, and then the R is down here. The paraboloid is up here. The plane is down here. And then the solid, those should have been in blue, that's okay. And then the solid is the D that's between those. So, what does this say about the integral? So, let's see what happens here. So we want the integral over that d of x dv. So this is the result. So I'll write this twice. I'll write it sort of messy where we put everything together, and then we'll write a final version. So the outer two integrals take care of r, right? So just to remind us, let me point out the r is over here. So these guys take care of r. So those will be negative pi over 2 to pi over 2. And in a function or near function, so r equals 0, and the far function is r equals cosine theta. The next one, these will be z's, and so this will be a floor and a ceiling. Now the kicker is, of course, for these, that they need to be cylindrical. So the floor, that's fine, that's z equals 0. The ceiling, that's z equals 3 plus x squared plus y squared, that becomes z equals 3 plus r squared. The integrand, which is x, that has to be converted. Then we have the polar r, dz, dr, d theta. So the integral, the final integral, if you like, that gets evaluated, negative pi over 2 to pi over 2, and 0 to cosine theta, that is the r. The floor is 0, z equals 0, the ceiling is 3 plus r squared. The integrand becomes r cosine theta, that's the x, and then the polar r is really an r squared, but I'll leave them separate for now, dz, dr, d theta. That's the final integral, and that just gets evaluated. It's not pretty at all, but it works. That's the final result. So let me do one more where I give a little bit less and there's a bit more to figure out. What I'm going to do first is I'm going to clear the screen completely, so take a look at this, look over it, make sure it makes sense, because we'll do a problem which is somewhat similar, same idea, but different problem. So, for example, let's say, suppose D is the solid, say inside the cone z equals the square root of x squared plus y squared, and below, let's say the plane z equals 9. We'll say the density at a point is f of xyz equals, say, x squared z. Find the mass. So abstractly, or symbolically if you like, the mass is nothing more than the triple integral over d of the density x squared z dv. So then we say to ourselves, great, okay, what does d look like? So let's draw d. So what we need to do is we need to draw d. We need to identify the floor and the ceiling. And then we need to identify the region in this case, because in this case there's no r given, right? Explicitly given. Right? So we've got this cone. The solid is inside the cone and below the plane, so it gets chopped off at the top, up at z equals 9. So this top, this is z equals 9. This bottom, this is the cone. It's the x-axis, y-axis, z-axis, and that's the solid. It's literally just a solid cone. So we have to ask ourselves, like, well, okay, what can we get out of this picture? So from this picture, interestingly, it's pretty easy to see the floor and the ceiling, right? So from the picture, the floor is the cone. And the cone is z equals square root of x squared plus y squared, which is z equals r. And the ceiling is the plane, and that's z equals 9. So another way, if it helps to think of the floor and the ceiling, is to sort of imagine that we had like a raindrop, and the raindrop was falling down through the object, so like here, and first it hits the plane, passes through the cone, and passes through the D and exits at the cone. So that's a good way of thinking, like, what's the floor and what's the ceiling in this particular case. Because the ceiling is the first thing it hits, floor is the second thing it hits. So the next question, of course, is what's the R? So here's another picture. In fact, I'll draw two more pictures. So we can see the R on this picture. And then I'll draw a separate R in the XY plane. So in the picture on the left, the R is the disk right here, because it's on this disk that the two functions are considered. So it's like a shadow. If there were a sun above the shape, it would cast a shadow, and this would be the shadow. This is the R on which the cone and the plane are being considered. So over here, of course, this is just a disk. Now, the note about this is you might say, like, how big's the radius, right? So if we say, well, what's the radius? Well, let's think about where the cone meets the plane, right? Because that's where this is. So cone meets plane when 9 equals the square root of x squared plus y squared. So x squared plus y squared equals 81. So radius is 9. So over on the right, we can just make this clear. We can draw a 9 here. That's the radius. So at this point, we can pretty much put everything together. Right, so we have the mass is the integral over d of x squared z dv. So the altitude integrals are for r. So that's 0 to 2 pi, 0 to 9. The inner, the floor, and the ceiling. So the floor is z equals r. Ceiling is z equals 9. The integrand becomes x squared z. So x is r cosine theta squared. Z stays the same. We pick up a polar r, dz, dr, d theta. So just in closing, let's just clarify these two guys here. Those give the r. That's the floor. Z equals r. That's the ceiling. Z equals 9. That right here is the polar r. And we have an integral, and then we just evaluate. And that's it.